Okay. In this video, I'm going to tell you about asymptotic notations. So, what are asymptotic notations? Now, there are actually three types of asymptotic notations which we normally deal with in time complexity concept. The one is big O of n, the other one is omega, and the other one is theta. So, for a particular function, big O of n denotes the upper bound of a function, your omega denotes the lower bound of a function, and your theta denotes the average case, that is somewhere between the upper bound and the lower bound. So, moving on to the first notation, that is big O of notation. So, the big O notation, if we have to define it, then for a particular function fn, for a particular function fn, to get equal to big O of gn, if for every positive value, for every positive value such that the two constants here, C and naught, for two constants, that if every positive value C and N naught, such that Fn is equal to C asterisk Gn for every N greater than N naught. So, what is actually the proper definition here? Now, this particular definition will be sounding you a little bit of tricky. So, let me tell you. The big O notation, first of all. Now, basically, in just the previous slide, I defined you the big O notation, that is the upper bound. So, upper bound will simply do it like that. The big O of no, the big O notation Fn is equal to OGN, that is the big O of Gn, if for every value that is Cn and N naught. Now, for every value that is every positive value, Fn is Now, ideally, this should be not equal to, but since we are discussing the big O of notation, then this should be less. This should be what? This should be less than. Now, when this is less than, this is your ideal case. So, let me take you with an example. What is this? Now, C is a constant here, Gn is a function. Now, when I take you to the, suppose if Fn is equal to 2n plus 3. So if we have to make it less than n, now what should be done here to make it greater than? So to make this particular fn less than this, so we simply take any constant value. It can be 10. So in that case, this is your fn, this is your c, and this is your gn. So in that scenario, time complexity becomes O of n. Now, so O of n becomes the basic kind of what it becomes. It simply becomes a basic standard. Like this particular is a particular GN. Now, below that, you can't go. You have to go for the maximum value. So you have to go for ON and above that because this is a maximum value. Below that, you can't go. For Fn equal to 2n plus 3, To make it less than, you can simply take it like you can simply take it 5n plus 3 kind of. Simply, you can take. C is a constant here. C is a constant here. So even if you take it, still this is also okay. Still the time complexity will become O of n. So this is the definition of wave O. So if I write the priority order here, what is the priority order? Priority order is O of 1, O of log n, O of root n, O of n log n, sorry, first, O of n log n, O n square, O 2 to the power n, O 3 to the power n, so on. So this order, and it increases in this direction. This direction it increases. So based upon this, now if we have fixed this O of n, then we can multiply here log n. We can multiply a constant value log n with this. We can try to take any of the maximum values, but we can't go below that to make it n log n. We can simply make it. We can multiply. We can take any of the values above O n in this order because initially here the gn was fixed as n, and we have to simply make based upon our definition of figure of like it should be less than. So for that reason we can do. So now coming to our next notation, that is omega. Omega denotes lower bound. What it denotes? It denotes the lower bound of a function. Now its definition is very simple. For a function, for a function fn to equal to omega gn, if for every positive value c and n naught such that, now here comes a change, such that fn is greater than omega of 2, and we will multiplying here c for every n greater than n naught. So if we go for the definition of a lower bound, that is omega. So for omega, if we have a function fn and if it is supposed to be equal to omega of gn, if What we'll be writing here? If for every positive value, what if for every positive value C and N naught such that Fn is greater than C into omega Gn, C into omega Gn, C into omega Gn for every N greater than N naught. So this particular definition is quite similar to what we had of big O of notation. So if we have to deal with this kind of thing, that is big omega notation. So how we do it? Now for this function to analyze with the situation, we will again be doing it. Fn, supposedly Fn is equal to 2n plus 3. Now, based upon our condition that Fn should be C asterisk omega Gn, that should be the case. So based upon this, if we write here Fn is greater than C asterisk omega Gn. So how do we do that? So we write here 2n plus 3 greater than n. This we know here. So this n simply becomes here. This is your Gn. Now we have to identify here. We have to identify here. Sorry, just for correction, it should be here simply Gn. Uh, Omega is not needed. Just to correct it. Even here as well, I'm just erasing this. Just for the correction, this can be like this was 10 here. This is here is correct. So that is okay. So everything beside that is correct. So here it will be C, the constant value, the positive constant value into Ga. So now we have to, we have got here function. This is your Fn and it should be greater than C asterisk Gn. So what we have to make in order to make this value, the value of Fn greater than this n, we can simply first of all multiply up 1 here. This will make it n. So this one becomes C. Now even for that also, what even for that also this becomes omega n. So now this question will ask that for that also it was big O of n. If for this also this is omega. Now the change lies here that for this omega, for big O of n, you could have taken the values higher in the priority order from O of n. The big O of n, you could have taken the values higher in the priority order in case of big O notation. But when it comes to big omega notation, it is a lower bound of a function. So in that case, you can only consider the values that are below the in the priority order. What? That are below in the priority order. So I mentioned it also for big O, values can be greater than the O of n, can also be satisfying the condition for big omega notation. The values should be less than equal to, it shouldn't be O, it should be omega here. It should be omega n. So This is the condition. This is the definition, difference what it lies. To show you with the priority chart as well, I'm going to write it here. Let me take it. Now here is the priority chart. Here is your value ON. When you write it in terms of omega, it will still remain the same. But what will be the difference here is that for big O notation, you could have considered the values O n log n, O n square, O 2 to the power n, and so on. When it comes to the context of big omega notation, when it comes to the context of big omega notation, you can only take the values lesser than in the big O, sorry, lesser than omega n or the values that lie below. You can take the value omega n as well as the values that below, like in the less priority order. Like you can take omega root n, you can take omega log n, you can take omega 1, but you can't take omega n log n when it is the case that its satisfying value, the function gn is n. Remember when the function is gn is n. So what I have written here, this, this value, these two are keeping in thought, these two are keeping in thought that gn, your gn is, let me write it more clearly. These values, this concept has been determined keeping in mind that your function, that is your gn, is equal to n. Remember this. So now we come to our next notation, that is theta. Now theta, as I mentioned in the start of the video, it denotes the average. It denotes what? It denotes the average. So average means what? It is somewhere between the lower bound and the upper bound of the function. It is somewhere in between the lower bound and the upper bound of the function, that particular notation. So, so for theta notation, what we will be doing here, how to write the Fn. So now Fn should be, now if theta denotes average, so average should be somewhere between the lower bound of a function and it should be somewhere between the upper bound of the function. Like it should be between the lower and the upper bound of the function as clearly. So how to write the lower bound? Lower bound was something called as C1 asterisk Gn, or I'm writing it more clearly. It is somewhere between C1 Gn. And what is the upper bound? Upper bound is somewhere C2 Gn. This Gn remains constant. Only the things that change are these two constant values C1 and C2. Now, which we already know based upon the two analysis, that is the big O and big omega. That for big O of notation, we have to determine a particular value of C, which will make the function Gn greater than the Fn. And for big omega, we need to take a constant value which will make the function Gn lesser than the function Fn. So therefore, the C1 and C2 values are different. Now, this analysis should happen for every n greater than n naught, where C1, comma, C2 and n naught are positive. They are positive values. So this is the analysis of the average case. Now, when it comes to the average case can be determined in simpler codes, in simpler program concepts, but average case is not that easy, can't be easily determined in every possible case. So, for that analysis, we normally do what we call as the big O notation and big omega notation. I repeat it again, average case analysis can't be determined in every program. It can be determined in simpler program segments. So more preferably, we do two notation analysis, that is big O notation and big omega notation. So this was all about asymptotic notations. Hopefully you got it. So thanks for watching. Do share and subscribe and stay tuned for more content.